In this very last lecture of chapter 4, we're going to examine the topic of relative motion. What is relative motion? Well, it is common sense that when it comes to quantities such as position, velocity, and acceleration, these kinematic quantities, the answer depends not only on the object being studied, but also depends on the observer. For example, consider this freeway, let's say 210 freeway or 10 freeway, running in the east-west direction. Suppose there is a car going this way, eastbound, at a certain speed, let's say 60 miles per hour, relative to the road. Okay. Now you consider another car going in the opposite direction, going westbound at 50 miles per hour. Again, measured relative to the road. Now, if you are a person standing by the side of the road, you're going to see the blue car going east at 60 miles per hour and the red car going 50 miles per hour westbound. But what if you're the driver of the blue car? Then you look at the red car, you will see the red car moving towards you, which is westbound at what? 110 miles per hour. Right? It's common sense. So you see the motion of this red car, whether it's speed, whether it's 50 or 110, really depends on who's observing it. The observer makes a difference. Okay, so there's no absolute speed here. It depends on who's observing it. So speed is relative along with other quantities such as position and acceleration. This is what's called relative motion. Okay, so basically it says motion is relative. The answer depends on the observer, not just the object being observed. Now, in general, let's consider a point particle P moving along this blue curve, okay? This point particle P moving along this blue curve. Suppose I have two reference frames. Usually I only look at one reference frame, such as the road or whatever other reference frame, but let's consider in general two reference frames. I label it SA and SB, okay, in the diagram to the left. Now, the center of the origin of SA is point A, and the origin of SB is point B. In reference A, the position P of this particle is denoted by the vector R of PA. Now I have to, we have to look at the convention of the subscripts here. RPA is a vector going from A to P. In general, if you have a vector that starts from point A and ends up at point B, then we label the subscript as R sub BA, okay, or point B measured relative to point A, all right? Let's say, for example, the vector RPA here, it is the position vector of point P relative to point A, so that's why we write it as RPA. It runs from point A to point P. That's the convention, okay? Similarly, the same point P measured by an observer at point B in a different reference frame, S sub B, is RPB. So it's the position of P measured by point B. Okay, clearly RPA and RPB, these two position vectors are different. How are they different? They're different because point A and point B do not coincide. Let's assume that point B is moving away from point A. Okay, initially they are the same point at t equal to 0. They coincide, but after time t, point A and point B are no longer at the same point, and point B moves away from point A at a constant velocity. Let's assume the velocity is a constant for now. V of BA, that's velocity of point B relative to point A. Okay, that's the same convention of labeling for the subscripts. All right, so that's the third side right here, the third side. So clearly, I have now a vector triangle, okay? Vector triangle APB. In this vector triangle, I know that RPA is the sum of RPB and the vector connecting A and B, which is V BA times T. Okay, now take a look at the convention again in the subscripts. Let's see if we can find some interesting rules here. Here is R from A to P, right? From A to P. So you measure point P relative to point A. Now, instead of measuring from point A to point P directly, I'm going to insert a point B in the middle. Insert point B in the middle. So instead of going from A, here's A, here's P. Instead of going from A to P directly, okay, I'm going to insert a point B in the middle. So I'm going to go from A to B first, and then I'm going to go from B to P. See that? Okay, so that's the basic idea. So I can insert between P and A, I can insert a pair of B's, So it becomes R of PB plus R of BA. Okay, so this is R of BA. And actually, I use V because I'm going to write T. But this whole thing here, V sub BAT, is just R from A to B. So I can write it as R of BA. Okay, and this is R of PB. Okay? So in general, if I don't use the labels in this diagram, in general, I have R of AC is R of AB plus R of BC. See that? I can insert in between A and C, I can insert a pair of B's, one here, one here. So that's the convention. All right. Now, once you know how the position vectors are related in these two reference frames, I can also find how the velocity and accelerations are related, because all I have to do really is take a time derivative of R with respect to time and get velocity. Right? So take ddt of this equation in red above. See, what do I get? Okay, then I get VBA, VPA equals VPB plus what? VBA. I'm assuming VBA is a constant, so I don't have to differentiate with respect to time, so I get this. Okay, so what did that tell you? How do you write this in words, this equation above? It says the velocity of point P relative to point A, measured by point A, equals to what? The velocity of the same point P measured by a different observer B, plus the velocity of B relative to A. All right, so that is how you find the connection of their velocities measured by two different reference frames for the same particle P. I can take one more derivative to get from V to what? The acceleration. Okay, so I can do that. Now, interestingly enough, if we did that, the first term, of course, becomes A of PA, right? The second term is V of PB, right? What's the next term here? Well, it's the derivative of VBA relative to time, respect to time, and that's 0 because I'm assuming that VBA is a constant. So you can have two different reference frames, A and B. Okay, they're going to measure for the same particle P. They're going to find a different position vector. They're going to find a different velocity vector, but they will agree on the acceleration of point P as long as A and B has no acceleration relative to each other. Okay, so A and B could both be moving. You know, A and B could be both at rest, or maybe A and B, they're moving relative to each other. B goes fast ahead of A, whatever. As long as they're, the velocity of B relative to A is constant. Okay, then even though they're going to measure different velocity and position for particle P, they will agree on the acceleration. This is a very important observation, because starting from next chapter, we will be seeing the Newton's laws for dynamics, and it is the acceleration that really plays a central role. Right? So that means the two reference frames will agree on the acceleration point P. And you will see from chapter 5 why this is so important. Of course, that's when the two reference frames, SA and SB, do not accelerate relative to each other. So the velocity VBA stays the constant. All right, so that's some general idea. Now, let's put it to use. You can think of many examples of relative motion. The example that I gave you above, 60 miles per hour versus 50 miles per hour, that's one of the simplest. But what I would do then is I'm going to only analyze one sample problem, but there will be different scenarios of the same problem. Okay, this is from the textbook. It's one of the more interesting problems of relative motion. And so suppose I have a boat which crosses a river, okay, which crosses a river. Now, if the river does not flow, assuming the river does not flow relative to the bank, so it's a stationary pond of water. And if you have a dock right straight across the river, and you want to reach that dock, right? So you start from one side, one bank, and you want to go to a dock right across on the other side. If the river does not flow at all, in which direction should you head the nose of this boat? Well, I mean, that's obvious, right? You just you just cross directly, right? So the velocity of the boat relative to the shore is just this, right across, okay? So this would be the velocity of the boat relative to the to Earth or the shore. It is also the velocity of the boat relative to the water, because the water does not flow against the Earth or against the shore, right? You would just, you just head the nose this way, and you're gonna get there. Now, on the other hand, what if the water actually flows? The water flows downstreams. So as the boat as you try to cross the river, perpendicularly, something is happening to the boat, and that is, it is being pushed downstreams by the river flow. So the river pushes the boat downstreams, adding another velocity. Okay, this is due to the flow of water in the river. So the boat not only crosses as this black vector indicates, it also moves downstreams as this blue vector indicates, and therefore it ends up moving this way. This is the actual direction of motion of the boat across. So eventually it's going to end up, here's the other bank, it's going to end up here instead of there. Okay, and this angle you can figure out. I'm going to have to label these vectors. Okay, I'm going to have to label these vectors. This black vector is the velocity of the boat relative to the river, not relative to shore. If it's relative to shore, it means it's going to actually end up over there. We know that's not the case. Okay, so that's velocity of the boat relative to the river. So if the river were stationary, it's going to get there. And then the river is going to carry the boat downstream. So this blue vector is the velocity of the boat relative to the shore or to the earth. That is v, river to earth. I'm using the same label as the diagram on the left. Now, what is VBR plus VRE? Remember the convention that we just discovered a minute ago? Okay, VPA, here's P and A, so you have P, actually I should use this V here. P and A, I can insert a pair of B's between P and A, so insert a pair of B's here, right? And the same thing here, between B and E, I can insert a pair of R's. So there's an R here, there's an R here. So this really is just V of what? B, E. This is the velocity of the boat relative to the earth. So this is the actual direction of motion of the boat. If you look at it from, from the side of the river, okay, on the bank, you see the boat moving this way. Okay, it's moving this way. So this is V boat relative to Earth, following the same subscript conventions as we saw a minute ago. You can find this angle. If I give you the velocity of the river flowing downstreams, and also how fast the boat can move relative to the water. So for example, if let's say V RE equals to 2 miles per hour. So that's how fast the water flows downstreams. And VBR equals to 4 miles per hour. So this is how fast the boat can move in stationary water. Then you have tangent theta equals to what? 2/4, which is 1/2. From that, you can find what the angle is. Okay, this is the actual direction of motion of the boat. So if you ignore the fact that the water current is going to carry the boat somewhere downstreams, and you just ignore that, you just keep on heading the nose of the boat right across, perpendicular to the flow direction of water, you are not going to end up where you wanted, which is here. You're going to end up somewhere downstream, which is there. Okay, so that's one case, which corresponds to the left side, the diagram on the left side, this diagram. Now, suppose you insist on getting the dock right across. You don't want to end up somewhere downstreams. Then clearly, you're going to have to head the nose of the boat somewhere upstreams, right? Somewhere upstream, and that is reflected in a diagram on the right side, this diagram here. So you say, okay, I'm going to head the nose of the boat to a certain direction, in a certain direction, which makes an angle theta with the vertical line, vertically crossing the river. Okay, so here is the direction you want to head the boat, head the nose of the boat. Okay, so this is V boat relative to water instead of right across, as you see here, which won't get you there. Okay, so you're going to do something like this. All right, and then this direction is perpendicularly across. So you have a dock somewhere here that you want to reach. You start from here. Okay, you're going to end up there. And you try to accomplish that by heading the nose of the boat this way, an angle theta upstreams. But in the meantime, the water flows downstream. So instead of ending up somewhere here, there is a water current taking you somewhere downstreams, and the velocity of the water current is like this. Okay, so you end up having an actual direction of motion like this. This is your actual direction of motion, which is exactly what you're looking for, because you can end up directly across over there. Okay, so this red vector is the velocity of the water flowing relative to Earth. So this is V relative to Earth, river relative to Earth. What happens when you add VBR and VRE? Okay, same thing here. VBR and VRE, you end up with this purple vector, which is V boat relative to Earth. Okay, just like here. And that's what you want. You want the velocity of boat relative to Earth to be directly across. And the water flows downstreams like this. Okay, and you want to go directly across. Now, what is this angle equal to? What angle theta should you head the nose of the boat to so that you will end up directly across? Well, again, if you're given these numbers, if you're given VRE equals to 2 miles per hour and VBR equals 4 miles per hour using the same numbers, then in this case, it's sine theta, right? Not tangent theta, it's sine theta. And that equals to what? VRE over VBR. And that equals 1/2. So clearly, we have to check the calculator. We know what this angle is. Theta equals 30 degrees. You need to head the nose of the boat 30 degrees upstreams so that it will eventually end up directly across. Okay, because it will be pushed downstreams by the water, and you will end up directly across. Okay, so these are two cases of taking a boat across the river. Again, the first case on the left-hand side, You ignore the water current flow, so you can end up somewhere downstreams, not directly across. The second case is you take the water flow into consideration, and you have to head the nose of the boat somewhere upstreams at an angle theta, so you can end up getting directly across. Okay, now, if I change the criterion a little bit, right? If I ask you this question, what if you don't care where you end up on the other side? Okay, it doesn't have to be directly across, but you just want to get there as soon as possible. You want to minimize the crossing time. You don't care where you end up on the other side. What is your strategy? What angle should you head the nose of the boat? Okay, should it be somewhere upstream, somewhere downstream, or directly across? That's the idea. Okay, that's the problem. Well, here's the thing. We know what happens if the river doesn't flow, right? We know the optimal answer is just directly across, right? Directly across. So let me actually write that down. To minimize crossing time. We know what happens if the water doesn't flow at all. It's going to do this. Okay, you are just going to do this. You position the nose of the boat this way, so you can end up somewhere right across. Right? Now we add the flow of the river into consideration. It will give you, it will give you a velocity somewhere, in this direction, right? And whatever that amount is, and you're going to end up, instead of directly across, you're going to end up somewhere here, right? You're going to end up somewhere here. So you don't. This is your intended destination. This is your actual destination. But does that matter? No, it doesn't matter, because I said I don't care where you end up. You just want to cross the river as quickly as possible. Question is, does this purple vector change your strategy? Should you readjust this blue vector so that it is not directly across? Rather, it should be somewhere upstreams or downstreams. Let's say somewhere upstreams, which means this way. Or somewhere downstreams, which means, actually, that's downstreams and this is upstreams, right? So either way, you're no longer heading directly across. Does that help with anything, with the presence of this river flow? Well, you think about it. Okay, either way, whether it's somewhere upstream or somewhere downstreams, you can break down this red vector into two components. Okay, two components. Let's say we take the red vector on the right side. Okay, so we break this red vector down into two components. Here is one component, and here's the other. Right? Now, each component is a little bit less than the red vector itself, isn't it? Let me amplify this red vector and its components, and you know exactly what I'm talking about. Okay, here's the red vector. Let me draw it more carefully. So here's the red vector representing the velocity of the boat relative to the river. Okay, and if you break it down to components along the river flow and perpendicular river flow, so here is perpendicular river flow, and here's parallel to river flow, right? Then clearly, each of these green vectors is shorter than the red vector, right? It's going to be shorter than the red vector. Now, which component will take us across? It's this guy. It's this guy right here. This is the vector that takes us right across. What we're doing by going somewhere downstreams is that we have shortened the vector which is being used to cross the river. This green vector is shorter than the red vector. Is that desirable? No, you're going to take longer time across. Okay, the fact that the water flows shouldn't change your strategy because water flows only parallel to the river. So whatever the speed of the river flow, it doesn't do anything to push you across because it's parallel to the river. The only way to cross is to use the engine, the power of the engine of your own boat, which means you should put 100% of the component of the velocity available to cross the river. And that means the strategy is to head the nose of the boat directly across. You are not going to end up directly across. You're going to end up somewhere downstream, but it doesn't matter. You still spend the shortest possible time crossing it. Okay, so that's a twist to the problem. Now, think about another twist, and that is, let's say we are in a competition. Okay, we're in a competition. This competition involves swimming and running. There are two parts to this competition. So here's the rule. The rule is, this is one side of the river, and here's the other side. The rule is you must start from point A here and end up at point B directly across. I want you to do so by a combination of swimming and running, okay? Swimming and running. So here's the line connecting A and B directly across. You know how fast you can swim. You also know how fast you can run along the bank. Your job is to find an optimum strategy based on your swimming speed, your running speed, and also the speed of the river flow, so that you can minimize the total time, which is running plus swimming, to get from A to B. Okay? Now, how do you do this problem? Well, there are two speeds that belongs to you. One is your running speed, the other is your swimming speed. So V, you have, let me write that down here. V swimming and V running. Okay? And then of course, the river also flows, V water. That's another complication here. If the water does not flow at all, VW equals 0, then what is your strategy? The strategy would be to head directly across. I mean, that's obvious, that's trivial, right? Because you have the shortest time, the shortest distance to swim over. Also, you don't have to run at all. You're already there by the time you get there. So that's how you would do it, right? VW equals 0. Now, on the other hand, the water actually flows. So if you actually head this way, you're not going to end up this way. You're going to end up somewhere downstreams. Okay? You're going to end up somewhere downstreams because the water is going to carry you over. You're going to arrive at point C here, right? So once you arrive at point C, what do? You have to run towards point B. Okay, this is so the first leg is swimming. The second leg is running. Now, if you can run really fast, what do you think your strategy should be? Well, if you can run really fast, yeah, you can end up at point C. Okay, by heading the direction of swimming this way, you have minimized the time it takes to swim, according to the strategy we just talked about a minute ago, right? To minimize crossing time. The bad news is that you're going to arrive at point C, not point B. But is that a big deal? No, because you can run so fast. So between point C and point B, you run, it takes almost no time to get there. So the strategy is still to head this way, okay? To head this way. You just have to minimize running time. And that is when VS, the swimming, that's when VR is really large. VR is much greater than VS, okay? So that is one possibility. Another possibility is that you can swim rather fast, but you can run very slowly. Let's say the other side is actually a swamp. So once you get point C, it's going to take you forever to reach point B. So clearly you don't want to do that, right? You don't want to arrive at point C because, you know, the second leg of is going to take too much time. You want to get to point B directly, so you don't have to get stuck in a swamp. You're already at your destination. So how do you arrive directly at point B? Well, clearly the strategy is to head this way. This way, right? As we saw earlier. So because you're going to end directly across. So you would steer, you would swim in a different direction now, upstreams. You're going to swim this way. Right? You would arrive at that point if the water doesn't flow, but because the water actually flows, you just end up at point B, which is perfect because you don't have to run at all. Okay, you run so slowly, but you don't have to run. So that problem is solved. So this side, this direction is for you to use if you can run very fast. That direction is for you to use if you can run very slowly. Okay, these are two extreme cases, right? In the real world, you know, you're running and you're swimming, they both have a certain speed. It's not like one is much, much greater than the other, right? So therefore, you shouldn't be adopting either of these extreme cases. It's going to be somewhere in between. Right? Your optimal strategy is probably somewhere in between these two cases. Let's say you head this way, you know, right? You head this way, you end up you don't end up here. You can end up maybe somewhere here because, you know, the water is going to push you back somewhere here. And then once you arrive at that point, you can run towards point B. Question is, what is this optimal angle theta here such that you can minimize the total time of swimming plus running that will get you from A to B? The answer depends on these three numbers: V swimming, V running, and V water. Okay, it's a minimization problem. And this problem is more involved than the examples we talked about. But it's an interesting problem to think about. And clearly, you know, the answer should be somewhere in between these two extreme cases. And I'm going to leave this as an exercise for you. In fact, as an extra credit exercise for you, because it does involve a minimization procedure using calculus. Okay, so that's something to think about. So this problem, you know, has a lot of variations. Once you understand how to do this problem, you're pretty much set with the idea of relative motion, and you will see more examples of relative motion when we get into dynamics later.